Now, is it better? Yeah, cool. So we are going to talk about interpretability of machine learning in this talk. So let me start with a highlight of the talk. Okay, so we'll start by introducing the problem. We will see why do we need explanations, the benefits. We're going to walk through the notions of explainability. And then we're gonna see like two of the main divisions, two of the main ways to explain models. So which is like white box models and post-hoc explanations. White box models, we're gonna give a couple of examples and discuss some of them. I guess like many of you have heard them. And then we're gonna walk through post-hoc explanations. And we're gonna give an example first in the domain of recommender systems. Walk through an example of counterfactual explanations, see one of the perturbation approaches in explainability, and then look at the limitations and how to evaluate them. So why do we need explainability? So explainability is actually, it's actually since the recent years, it has been becoming quite more needed and dominant in any discussion, because of the wide adoption of AI systems. So like we see AI systems adopted everywhere, from autonomous driving, medical diagnosis, loan predictions. And wherever we have some high risk decision making scenarios, we actually need to give a reason and to yeah. Mm. Yeah, is it? Cool. Okay, thank you. So there is actually becoming, explainability is actually becoming a societal need, and more and more becoming also legal requirement. So as a point of reference, we can talk about the GDPR, which was released in 2016. And one of the points of the GDPR was actually that it was stipulating the need for giving meaningful reasoning of any AI-driven decision making. So this was referred to as a right to explain. So, but beyond kind of like the needs for, let's say, regulators or showing a bit of transparency, we also have to think about ourselves a bit as developers of these systems. So we actually need to make sure and understand how these systems are working. And we actually need to know how to debug them, and if we are building a system that is showing some sort of bias. So, okay, so let's think about this across the different industries. For instance, in the advertisement industry, so there is always a reputational risk that comes with like using AI systems. We could actually place some adverts with content that doesn't fit to the brand of the company. Or if we think about health, I mean, like nowadays AI is actually very good at making medical diagnosis. And however, when we did this study a few years ago, where physicians were a bit anxious, actually 49% of the physicians in the States were anxious and uncomfortable when using AI. But also think about the finance system. So when somebody is applying for a loan, so you apply for a loan, you get denied a loan. So, and this is actually becoming more and more, it's happening more and more every day. So loan systems are based on features that characterize like income, or credit scores, and everything is happening automated online. And you get like a denied loan, but well, you are entitled to understand why this is happening. So there are a lot of advantages in having explainability, starting from a transparency. So we are able to understand, to see how the model works. We are able to scrutinize it and debug it if needed. And also users of the systems start trusting the system. So it's actually quite good because, well, we increase the fidelity of usage of any system. It's effectiveness. It's actually, and also efficiency. They are tightly related. So an informed information, it's easier to accept, and it's faster for the user. It's easier and faster to make a decision. There is a bit of risk of creating persuasive systems, actually. So that has to be kept under close eye. And there is a satisfaction. So think about everything that we just mentioned before. So like the user experience is increased because like you are showing how the system is working. So there is also a risk with transparency that I didn't mention. So from an industrial perspective, if you are too transparent, actually, you might show sensitive information about your system and how it works, and lose your competitive advantage. So there is also whenever you are building, or we are building, explainable systems for industrial applications, we should be a bit cautious, and we should be aware of how much we can show and not show. And there is this thing though. The explanations are hard, and the hardest models actually are the hardest to explain. This is actually referred to as the sometimes flexibility, explainability trade-off. So the more complex is a model, so the better, the more flexible a model, the better they will perform. So if you think about deep learning models, they will perform quite well in terms of accuracy and predictive power. But what is happening that we are turning these models into, so we are adopting models that we are unable to understand. Whereas like simple models are quite easy, are understandable, and however we are losing the explainable power. And research nowadays is happening and is actually trying to shift this curve. So all the research, there are two ways. We either are trying to move this curve to the right side, so by using approaches as post-hoc explanations. So we're training a model, we are generating predictions, and then we are trying to explain what the model did. Or we are trying to move this curve up by creating more explainable and understandable models that are even better predicting. And there are a lot of challenges in explaining because, well, it's not only the hardest model is the hardest to explain, but also we have like a lot of notions. We have a lot of requirements depending on the domain, depending on the stakeholders. And we have a huge plethora of approaches, spanning from applications of ML and recommender systems and NLP, etc. On top of everything, we have different stakeholders. So, and everybody has their own requirements. So, well, when we are crafting and building explanations, we are targeting a user. Now, the user, the stakeholder, the person who is receiving this explanation might be categorized in different groups. So, for instance, a data scientist might have different requirements from everybody else, but also they have like different expertise, so they can understand more complex formulations or more complex explanations. So, and they have different requirements. So the reason why data scientists want an explanation is because they want to understand the model, they want to be able to debug it, and they want to be able to improve upon it. So then we have the business owner who might not have any domain expertise, but they still want to understand the model, and they want to make sure that it is actually it's actually a good fit to the policy or to the scope of the company and the brand. And they are actually the people that are approving this model. So we need to be able to explain them to the business owners. But there's also people who are going to test the model, check for risks, and try to understand if our models are actually robust enough for production. And regulators. Regulators are making sure that there is no bias involved in deploying a system. And finally, we have the user, actually. The user who is the group that is being impacted. So the user is denied a loan. Why am I denied a loan? So they have the right to understand why they are denied to get a loan. So let me first go through 3 of the notions of interpretable system, of explanations. So we divide them in interpretable systems, in comprehensible systems, and opaque systems. So interpretable system is actually a system where we can understand the inputs and we can mathematically map the input to the output. And it's actually pretty easy to understand for everybody. And here we can put like things as regressions or support vector machines. Then we have a comprehensible systems. Those are a bit more complex systems. So there is actually, there's still an understanding, but the model is actually emitting signals and requires the user to be sort of domain expert in order to understand what the model is doing. And then we have systems that are opaque systems. So these are the worst. So we don't know what they do. So they do it. They might do it right. They might do it wrong. We don't know it why. So now the challenges that are going on in the domain of explanations is actually here. So here you can see on the topmost the so comprehensible system. So it's actually giving some hints of like the signals that the system is using, and still it's requiring some domain expertise to map it and figure it out, the reasoning why. It's not fully human understandable. But it really requires some expertise to understand. But it's still kind of like there is some so the domain expert can map and understand a bit what's going on. On the right side, we have the interpretable system, which it's pretty easy to understand. So it's using one of these classes that we mentioned before. So like it might be a KNN, it might be a regression, and it's understandable. So a user generally, and there has been a lot of studies to see, for instance, decision trees are thought to be one of the most understandable type of approaches by users and even non-domain experts. And opaque systems, so now the challenges that are happening in opaque systems is actually we are trying to move them either to the comprehensible systems or we are trying to move them to the interpretable system. So there's actually, going back to the curve that I mentioned, we are trying to shift it either to the right or up. So still, as I mentioned before, even an interpretable system kind of like is giving us the signals that are yet to be mapped. So we need to build a node, so we can build systems, actually reasoners, that can give us an explanation which is human understandable. And going back to the curve, so we have opaque systems which are actually standing on the top right side of this graph. And we want to make them more understandable. Now, how do we make them more understandable? So let me start by showing you 2 of the approaches that we can use. So we can classify them in white box approaches, or so usually throughout the literature you see that to those we refer to them as intrinsic explanations, sometimes white box explanations, and post-hoc explanation. So an intrinsic explanation is actually a model which is deemed understandable. It's easy. So it's a family of It belongs to decision trees or sparse linear models. And then we have post-hoc explanations. So these are applications that interpret a model after it has been trained. So we build a model, whatever, and we grab it as a black box. And on top of that, we build another model to explain this model. So white box models. Now, in white box models, we can mention things as association rules, we can mention linear regression, logistic regression, decision trees, rule fit, naive bias, and k-nearest neighbors. And we can mention more, but it's just to get a gist. And we can use them for a lot of tasks as regularization, classification, and some of them are even used for recommender systems. To mention a few, k-nearest neighbors, association rules actually, and also logistic regression. Now, here we can see them. So you see some examples of explanation that we can generate with them. So on the leftmost, we see the linear regression. So where we see like we are learning the weight actually, so the parameter. And we say that if we have a unit increase in one of the independent variables, we will see an increase of the weight associated to that variable to the predictor. So then we have decision trees, which are straightforward. We are actually creating what if scenarios. And so each node in the decision tree will be a what if, and so what if condition 1, 2, 3, and we don't go down the decision tree actually, and then we make a decision. So we have k-nearest neighbors, which is just a proximity explanation. Then we have linguistic or rule set models. We have GLMs, and then we have, I will give an example of GLM afterward. And also then we have the Bayesian models, where we are required to make an assumption of independence, and then we can use the individual contribution of each feature actually to make a prediction, and use that individual contribution actually to explain the prediction. So let's give an example. There's actually, let's suppose we want to compute the daily coffee intake as a function of stress, sleep level, and whether we are going to work. So, and we are computing stress and sleep as we are drawing them uniformly actually from uniformly between 1 and 10, and actually for work it's a yes or no, and we draw it with a 50-50 chance. And then we use, we can actually draw the number of coffee from a Poisson distribution, and we can model the intensity as a function of the 3 features that I just mentioned. Now, surprise, surprise, we cannot explain this or predict this thing with a linear regression, but we can do it with GLM, right? So these are generalized linear models. Now, what happens is that we need actually to define a link function. So this has to happen manually. So then we need to define a probability distribution that is coming from an exponential family, and then we have the weighted sum of the parameters that we want to learn. So in this example was simulated, so we know actually the distribution of the, so we know the family of distribution, we know it's a Poisson distribution, and we know that the link function is going to be a logarithmic link function, right? So what happens is, like, we are computing, we are learning all these weights actually associated to stress, sleep, and work. However, there's actually, we cannot use the weights directly, but we need to do a bit of massaging. We need to transform actually predict the hypothesis. So, and the transformation is going to be like we are exponentiated both sides. And now what we end up, in order to get like the conditional expectation of drinking coffee, is going to be a function, an exponential function to the parameters and the features. So which means like the explanation in this case is going to be like the increase, for instance, in the stress level by 1 point it's going to have a multiplicative effect on the expected number of coffees that one's going to drink. And this multiplicative effect is going to be by the stress level, the expected parameter that is learned here. So here, yes, you don't see the laser. So it's going to be like this factory. And the same goes, the same explanation is going to be given by the sleep and by the work. And this example just to say that, I mean, like there are advantages and disadvantages. So, and to mention some of the advantages, we can see that this sort of models are sometimes easy to explain. We have a lot of approaches. We have a huge community that is implementing these approaches in any of the coding languages that you might imagine. In some domains, these approaches are yet considered state-of-the-art. In some of them are not considered state-of-the-art, but they are very hard to beat in industrial scenarios. For instance, just to mention recommender systems, when you think about productionizing recommender systems, approaches as can, and there is quite a lot of research saying that, well, don't do research on deep learning sometimes. And because like some of these approaches are very strong and they are explainable and very hard to beat. And so another advantage of having these models, this type of approaches, and doing research actually in moving forward, in moving upwards, the flexibility, explainability trade-off, it's actually that we don't have no additional training step, as we will see with post-hoc explanations. There are some disadvantages, and the list is not limited to what I'm mentioning here. So we can mention that, so as we saw before, so we need to handcraft nonlinearity, or also interaction effects have to be handcrafted. So the developer needs to have some domain expertise. So there is also a limit to how explainable these models are, because like at the end, if we have like a million features, there will be a limit to how much the user, the data scientist, but also the consumer can digest. So these are cognitive limitations actually. And so all these models rely on assumptions as well. So we need to make sure that we are getting these assumptions correctly. So as mentioned, we go again, it's always about this curve, actually. So we just talk about like the rear end of this curve and how these models are explainable, they make sense, sometimes they are very strong. However, we have like a huge plethora of research, the left end of this curve, actually, everything that is going upwards. And those are models that are very hard to explain. So, well, lucky for us, there exists research, and these are usually explained by means of post-hoc explanations. And there is nowadays there is a large plethora of ways to convey explanations for post-hoc models, starting from, visualizations where we can perform some sort of like dimensional reduction and display embeddings actually, and try to reason about that. There is model simplification approaches. Model simplification is probably quite interesting. There is a paper from Falunieri et al. On paramount. They are assuming that decision trees are similar in how similar to deep neural networks, and they try to simplify the reasoning of deep neural network while training a decision tree and maintaining a high fidelity. And then we can actually generate linguistic explanations, then we can have feature importance explanations, and more. I mean, an example, we'll see them. So, however, there are three desideratas that we want about this model. So, like, we want these models to be, in general, we want them to be model agnostic. And we want them to maintain fidelity. So we want the model to, they want them, we want them to be flexible. So we want this model to work with any model. So we have like a deep neural network, we have like a recurrent neural network, and we can use the same explanation technique that works with both of them. So we want them to be flexible. So we want them to show us different types of explanations. And we want them, we want them to be explanation flexible, and we want them also to be representation flexible, meaning that we can work through a large plethora of features actually, and digest the large plethora of features to generate explanations. So in general, these approaches are categorized in three main branches. So we have example-based explanations. So example-based explanations are a specific type of explanations where we are using particular instances of the data set and we are trying to explain the behavior of the model by looking or explaining the underlying data distribution. And some examples are KNN association rules and counterfactual explanation, and I have prepared a couple of examples for them. And then we have global or local explanations, which are trying to explain the average behavior of the model. And then we have local explanations. And local explanations are quite interesting, actually, and there is a lot of talk about a lot of research recently about them, which are trying to explain the individual behavior of a prediction. So for each prediction, we are trying to explain it, and we are actually trying to explain the model in a local proximity, and I have prepared an example for that. So let me start with association rules. So an example on, there's an example coming from recommender systems. So if, so recommender systems are, are systems that I don't know if everybody has heard of them. So maybe a quick introduction. It should be English. So these are application of AI systems that use past behavior of the user in order to predict their preferences. So, for instance, whenever you go to Netflix, so all the items, all the movies that you see on Netflix are actually generated with AI systems. So the ranking of these items is generated with the recommender systems. But it's not limited to ranking items. It's also, for instance, again, on Netflix, if you think about the carousels that are displayed on the web page, even the ranking of these carousels is actually not random. It's actually tailored to every user. So, and these are recommender systems, and these systems are everywhere. Once you see them, they are everywhere. So on Google, Amazon, every email you get, on Expedia, the carousels are actually personalized. The filters are personalized. So they are everywhere. And this example is a simple example of using association rules to explain. So we have a black box model, which is generating a tailored recommendation to a user. So user has clicked on few items, and we know the history, the preferences of the user. Then we learn some embeddings about the user, so the model can be complex. I mean, like we learn some embeddings, and for all the items in our catalog, we generate some predictions. And we rank these items based on the highest score that our model generates. And we see there in the right example, we have, for instance, this user might be Back to the Future, might be the best item for them. And the second item is it Men in Black? Yeah, Men in Black. Now, how do we explain these items to the user? So in a recommender system, there are different paradigms of explanations. They can be divided in item, user base, and now there is research going on in more semantically rich explanations. But for instance, there's an example of item-based explanations. So there's a family of explanations where we use past interactions of the user to explain it to them. So what we are saying is like we are recommending you this item because you have seen item, what is it, Star Trek and the Matrix. And the model is actually understanding that, so the post-hoc model is understanding that there is some sort of like relationship between the recommendation and actually the explanation. So the association rule is a simple model. It's just computing support confidence. So it's computing kind of like how many times these pairs have appeared overall, how many times this pair has appeared for this user, and this ranking actually these pairs of items. So the pairs being the item that the user is being recommended and the item in the history of interactions of the user. And it's ranking and displaying these interactions actually to the user. And we can actually, when using association rules, and it's also using lift. Lift is a combination of support and confidence, but we can use these three metrics actually to rank items based on how many times they appear together in the history of the user interactions. And for every recommendation, we need to repeat this post-hoc explanation, and we can learn actually to explain a recommendation to the user based on these past interactions. And these are usually deemed understandable explanations in the domain of recommender systems. And this model is actually interesting because in the original paper, so there exists an implementation in one library called RecExplainer that I co-implemented with a few colleagues a few years back. And it's interesting because this model was at the time evaluated by means of fidelity. So, and then the authors were measuring how many times this model is actually able to explain a recommendation generated by a black box model. So here we see again the recommendation model. The recommendation model is a matrix factorization in this case actually, and it's computing a score for each item in the data set, and for each user it's generating these recommendations. And then afterwards, we actually, for each recommendation, we are computing for B, C, and D. So recommendation B, C, and D. We are computing actually the association rules and ranking them by support confidence and lift. And then we are using actually these items in the past interactions of the user to explain each recommendation. And moving on to counterfactual explanations. Those are very interesting actually. So these are considered to be one of the most understandable types of explanations, because what we are doing is actually we are creating what-if scenarios. And so we are also describing causal situations. So if X had not occurred, Y would have not occurred. So this is very interesting. And this sort of explanation are, well, there is an approach, there are several approaches, but one that I particularly like is actually performing perturbations to the input to generate different outcomes. So that when the model or classifier is fed this different perturbations of the initial output, is actually generating a different classification. And so one characteristic that initially wasn't there in the first years of this research was that these models were not developing diverse enough explanations. So the perturbations were actually, the perturbations that were actually happening around this decision boundary. And what was happening was that all the explanations were similar to each other. To explain it more in detail, so this research was initially explained by Watcher and then extended by Motihan. And what they do is actually so we have a model, whatever is the machine learning model that we want to explain. So whatever is the machine learning model that we want to explain, we have a set of features actually. So an instance, a data point, and so this sort of explanations, I forgot to say, so this sort of explanations are generated per each prediction. So we have a specific data point, we have a client, and the client has a set of features, and what we are doing, we are generating a prediction for this client. And then we want to, the client, the prediction for the client is unsatisfactory. So we want to generate a different set of, so we want to explain why this didn't happen and what they could do actually to improve on that. So what we do is actually, we have the initial model as trained, we have the initial prediction, and what we're doing, we are actually perturbing the set of features. So we are making small changes in the feature and trying to see whether they're generating a change in the prediction of the model. And then we want these features to be as close as possible to the original set of features. So we use a distance function. The proximity distance function might depend on the case, specific case. So some choices might be, for instance, L2 more would be like the mean average deviation from the original features. Well, it depends actually, those are very specific. And then we want, so as I mentioned before, a desiderata of this type of explanation is that we want them to be different from each other. We don't want them all to be the same. So we are actually trying to diversify the set of explanation. And this approach is a greedy approach. So it starts by a small a very tiny perturbation from the original set of features. And it's trying actually to figure out all the counterfactual explanation that might make sense to the user. So to give an example, here, as using this approach, we see that the original input, the model is predicting that this user has an income below 50K, and the user has this feature, is working 45 hours, is a grad, it's working service, it's private, it's white, so it's using also personal features, so the model is probably using also the sensitive features of the user. The age single and the gender is female. So now we see actually the first result of these perturbations in order to change the prediction is that it's saying the user needs to get a master. That's okay. The user, so this user has to be 65 years old. And well, the user might wait another 43 years. The user needs to get married. So apparently, well, they have to do something about that. And the last one is showing a bias, actually. And this is quite interesting because like this is very powerful because like this is unexpected. So this model is demanding the user to get, yeah, you get it. So this is wrong. So this goes back. So the use of this sort of models is actually telling us that we need, there is something wrong with our model. So the original model. So we need to look deeper into it and see whether we can mitigate these biases. And the diversity that I mentioned before. So we need to show different circumstances. But this sort of explanations, I guess, like these cases are not some explanations that can be given to an end user. So that requires the model to be vetted furtherly before being deployed to production. And there is quite some risk whenever we are involving some sensitive data actually in modeling. And then we have surrogate models. So surrogate models is quite interesting. So we cannot, so the problem is like, how do we explain, can we explain the model in the entirety, but the models are quite large actually. So, and the decision curves can be quite complex. But what if we focus on a small region? So if we look closer, so these regions start to become linear actually. So instead of trying to explain the entirety of the model, we just try to explain the model in a local region around a particular point. So we have a prediction and we start trying to generate an explanation around that prediction. And yeah, so let's define Lime actually. So it's still, we want to learn something. So what we want to learn is we want to learn, so we have an instance, we have an instance, a set of features that we use to generate a prediction with model F. So then we have an interpretation model, which can be any of the linear models that white box models that we talked about before, actually. So we can use them to explain another model, which is non-linear, but it might behave linearly in small proximity. And then we need some measure of loyalty, actually, which can be like some sort of like, it could be any kernel, and I have an example afterwards. And we need also a complexity measure. The complexity measure is actually telling us what's our cognitive limitation, how much complex can be our explanation. So, for instance, if we're using superpixels in a classifier using images, so how many of those can we digest? So, and it's an optimization problem now. So the second thing that we need to do is actually we need to figure out a way to interpret our data. And so we need to figure out a way that to serve this feature. So this could be very simple things like, well, we have a binary vector indicating the presence or absence of a word actually, or in an image you can have, so images, we can group images by superpixels. So it's a large group of pixels, and you can say it's this pixel is available or not. So we can map them to an interpretable representation. And then the last thing that we need to do is actually we need to start perturbing or sampling around these explanations. So we have the new explanations, we start changing the explanations. So we start, for instance, doing small samplings of this feature. So we have a 1, we make it a 0. We take another superpixel, it was a 1, we make it a 0. So we make perturbations and sample around the original explanation. And then we have a new explanation now. So this explanation will be a small change to the initial explanation. And we need to reverse it back to features that can be used by the model to make a prediction. And then we feed them to the model in order to make a prediction. And then, for instance, an example here is we are using a linear regression actually to make explanations. In this case, so our explanation function is a linear regression. We want to learn these weights here around some sort of explanation. So then we are using a distance actually to keep the explanations, the new explanation very close to the original feature. So the new features very close to the original features. And then our loss function will come in place actually. So we're using this kernel and we are using a mean square error. And then we are using the k-lasso in order to reduce the set of explanations, the complexity of the explanation percent. So this would lead to some examples like this. So let's say we want to have like 5 words to explain our models. So we learn the following weights for our models. So we generated a prediction. The prediction is using a set of data, and it's saying, okay, so well, here we are predicting your essays. Then you're giving like the weights actually, and then it would be exactly the weights that led actually to predict this clause. And this is coming from the linear regression that we presented before, the superpixels actually, that I mentioned just before. Now, there is one issue with this sort of models. Now, we are performing a lot of perturbations of the original output. And what is happening that we are actually, so if we look at the blue points, this example is coming from the Compass data set, which is using some, it's a data set coming from it was a jail in Florida. It was a penitentiary system, and they were using actually sensitive data to make predictions about the classifications about criminal, and it's using actually sensitive data as racial indicators. And if we look at this data set, so there's actually, we took the features in the paper, the authors took the features, we did PCA transformations of these features, and there's a 2-dimensional representation of the data set. And we see in blue, actually, there's the original data set. And the red points are actually the perturbations of the original data set. And this is actually showing that when we are performing a lot of perturbations of the original data set, what we end up having perturbations that are out of distribution compared to the original data set. And there's a problem because, well, now we can figure out what is the original data set and what is not the original data set. And we can trick, for instance, perturbation-based models in explaining models that are biased by saying that they are not biased. So, and this can be done by actually, we can do what we can do actually. So this example is coming from the paper of Slug. And they have an original biased model that we want to deploy to production. And they want to give this model to a customer or regulator who uses post-hoc explanations to verify the validity of the model. And in order to hide the bias of the classifier. So the goal is actually to hide the bias of the classifier. And so we want to build a new classifier actually that can hide this one. And then it's pretty easy. So what we can do, we know the data points that are coming from the original distribution, and we can build the scaffolded classifier. So whenever we have a data point that is coming from the data, the original distribution, can just serve the original classifier, and every time we have a data set that is coming outside of this distribution, we can use a different classifier to predict. And this is an adversarial attack that it's quite easy to deploy. And how we do it? Well, in order to figure out which data point is coming from the original distribution or not, we can build another classifier which can say, okay, your data points are coming from the original distribution or not. And then we can serve this classifier to the client. And it's trivial, actually, but it's smart as well. I mean, like, it doesn't need to be complicated to be smart. And this leads for, in this example, the authors were explaining Lime. So they show actually, so they were using Lime to explain this model. And so you see that the original on the left side, it's actually using racial indicators to say, to classify users. But when we used Lime, actually, when the authors used Lime to explain the prediction with this scaffolded classifier, they can see that, well, some unrelated features that the author generated actually was someone explaining the predictions. And so this actually leads to a conclusion that perturbation models are not sufficient to test whether a classifier can discriminate on sensitive data. So a bit of pros and cons. So it's so having post-hoc explanation is advantageous because we don't need to rework the black box model. They work on any sort of data. So we can actually keep explanations short or complex. I mean, like, and we can have contrastive explanations. And we can use actually different features. If we have a change on the model, we can use different features actually to explain them. So these are quite powerful. Now, there are some disadvantages as well, and it's not limited to the list that I'm presented. But I mean, like, we don't have an additional training step. So we have an accuracy interpretability trade-off to worry about. So not everything can be explained by these models. So sometimes we end up having like no explanation for predictions. And the feature perturbation can be manipulated to hide biases, actually. And we have instability in explanations. So these models, every time we rerun for the same data point, we might end up having different set of explanations. So said that, we need actually to evaluate these models and make sure that these models are behaving, are resilient. And we have 30 pillars around evaluation of these models. But there's actually still, in my opinion, a greenfield of research. So there is a lot going on and there is a lot that can be added. and this is actually limited to perturbation models, but this should spread beyond them and spread also in domains as recommender systems. So we want the explanations to be faithful. So what it means that actually, if we are generating an explanation of a data point, we want it to be the same as the underlying model. So we want them to be stable. So small perturbations of an instance should not change the explanation drastically. And we want fairness, counterfactual failures. So an explanation preserves counterfactual fairness is the explanation corresponding to a data point and its sensitive feature perturbations are similar or dissimilar if their model predictions are similar or dissimilar. So a more formal definition. So here is faithfulness. So we have the original model, then we have the explanation to that data point. So then we have a mapping, actually a masking function that is grabbing the explanation and converting it back to the original features. And we input that explanation to the model and generate the prediction. And we want these explanations actually to be very close. Then we have stability. So we perturb the explanations and we want these explanations to be close together. And finally, counterfactual fairness. So we have an explanation, we have an original data point, we have an explanation, we have its perturbation, and we generate predictions actually, and we want them, if these explanations are similar, we want the predictions of these explanations to be similar or dissimilar. So to conclude, we walked through the problems of explaining machine learning models. We walked through white box models. We introduced post-hoc models, their limitations actually, and we saw the 3 pillars of evaluating explanations. And I'm open to any question.
Hi, question on your slide. I want to know more about the opposite of this. So if we identify that, if we find that adversarial algorithm that's what next?
Well, thank you. I mean, it's, yeah, you figure out that your model is actually fooling us. And, or it might have happened that it was like an innocent model, you know, you build an ensemble of models and this is happening for some innocent reasons, right? So what you want to do is actually probably rework your model and reduce the bias. And you want to evaluate it further actually before going to production with your model. And what you can do is actually you can perform extensive evaluations by means of, well, the 3 pillars that we just mentioned actually to make sure that it doesn't go, so that it doesn't generate an error of that. But I mean, like this sort of explanations are happening on a specific prediction. So another way you should evaluate it further is actually to run some user studies and to evaluate them with like a larger pool of beta testers, right, before going to production. And you have to make sure like the data scientist, the product owner, they have to make sure that the models are not biased, that we don't want to put them to production. So, and if it is a malicious model and it has malicious intents, it has to be reported. Good question. So, models
data that you can see where it's focusing on the image focus super pixel. So is that also part of recent way implemented capability, or does it fall within?
I guess you're referring to heat maps. Like
Yeah.
you see, so there are different approaches to generate this heat map. So it really depends which one of those you are using. I know some of them that are coming from our post-hoc explanations actually. So it's generally the one that I'm aware of. They are falling under the post-hoc explanations because you are building a separate model actually to explain the behavior of your original model. So we didn't go over them actually because also I work more in user modeling rather than in computer vision. But these are models that are generally fall under the post-hoc set of explanations.